Right, sorry, that was not the last question. This is in fact the last question, and it's a very, very interesting one. So the question asks whether there exists a countably infinite number of uncountable sets such that no two sets have a bijection between them. And this is like a mouthful, like it takes up way too much of my page. So let's try to translate that into like a slightly more sensible way. So if you want to ask that no two sets have a bijection between them, the only way to have that is for one of the sets has to be larger than the other. So you must have the cardinality of, if let's call our sets S, so you must have the cardinality of like Si is less than the cardinality of Sj. And because it's asking for a countably infinite number of such sets, so we must have one for every integer. So we must have S0, S1, S2, up until the end. Countably infinite number. And one natural way to think about this is by saying, well, if we can get a sequence so yeah, the idea of Si being less than Sj corresponds to the idea that you sort of want to have increasing cardinalities. Sequence so the idea is that we want to get a sequence of increasing cardinalities. And if you have a sequence, then you can just say, well, all of the terms in that sequence, because it goes on forever, form my countably infinite set. And because we have increasing cardinalities, no two sets have bijection between them. So yeah, that is a way to sort of parse this question into something a little bit more concrete. So first, so we can define it piecewise. So for S0, a sensible starting point is our sort of simplest uncountable set, a set of real numbers. Yeah. And so then, what should S1 be? Something bigger than R. And what's sort of natural way to get, what's a natural way to get a set that's bigger than some input set? And we saw in the notes that power set of X has cardinality strictly greater than the cardinality of X. So P of R is a set with its cardinality, the cardinality of the power sets of R is bigger than the cardinality of R. So we can say S1 is equal to power set of R is equal to the power set of S0. But then we realize, oh wait, we need to keep doing this infinitely many times. So how do we get a set that's bigger than S1? Well, we can say S2 is equal to P of S1 is equal to P of S0. And we can write this as like P squared, because we're applying the power set operator twice. And because this thing gives you a set, you're allowed to ask for the power set of it, so we're allowed to chain operators like this. So we can just say Si is equal to Pi of R. And so in this way, it's fairly straightforward to specify that because you have a sequence of ever-increasing cardinalities. So if j is bigger than I, Sj is bigger than Si, and so no bijection. So we have no two sets of bijection between them. And we can apply the power set operator countably many times because what you're putting up here is like a natural number. And we know there are countably infinitely many of those. And each set is uncountable because the base set R is uncountable, and after that we only ever get bigger. And so we know that our sequence, by constructing a sequence, we've essentially constructed our set. So for completeness, we'll just say S is equal to the set of all elements, where each element is Pi of R for I is a natural number. So clearly this is bijective bit of natural numbers because for every I you get an element of S. And so we have countability, and so we have exactly what was constructed. So true, such an object exists. That was a little bit of a mouthful, but hopefully it's clear that by starting with this very abstract thing of like countably infinite numbers such that no type of bijection between them, you can translate that into like realizing, oh wait, what we really want is like a way to construct a sequence of increasing cardinalities. And after that, building up the sequence piecewise leads to meaningful answers because you're answering smaller questions about like, okay, how do I get from a thing to something that's bigger than it? And then how can I like iterate that process as many times as I need? And you can see that sort of iterating an operator a natural number of times naturally falls under this idea and leads to this quite nice set, because even though we did a lot of work to get it, it is very nice and compact to describe, which is satisfying.